Hello everybody, I'm Julius Hülsmann, and in today's talk I present ARTC, an algorithm that automatically tunes read time tolerances for read sharing on edge devices. In distributed sensor networks, a single sensor device typically serves multiple queries simultaneously, despite having limited computational capabilities and restricted bandwidth. Conducting sensor reads independently for each query potentially results in a high CPU load on the sensor device, decreases the scheduling precision, and strains the network. Read sharing techniques mitigate the negative impact of running multiple queries by scheduling fewer reads that they forward to multiple queries simultaneously. However, conducting fewer reads inevitably worsens the quality of the sample data. Existing read sharing techniques do not adapt the extent of read sharing to the data's variability. However, this is vital to maintain the desired data quality, especially if the gathered data behaves very unexpectedly. In this talk, I present the adaptive read sharing algorithm ARTC, which increases the potential for sharing reads based on dynamic properties of the gathered data according to an application-defined data utility. We evaluate ARTC on real-world data and show that it reduces the sensing error by up to 60% compared to existing approaches with the same number of data reads. Today's talk is structured as follows. Firstly, I introduce the high-level view of ARTC and the challenges we had in mind while designing ARTC. Afterward, I continue with a detailed discussion on the building blocks of ARTC, also providing details on the data acquisition framework in which we utilize ARTC. Lastly, I present the experimental results, which we conducted on multiple real-world data sets with our open source implementation, and then conclude. The user configures ARTC with a single parameter, which indicates the permissible inaccuracy of the data representation relative to the data's average magnitude. We leave this value for the user to configure because applications differ in their tolerance regarding such inaccuracies. For example, an area monitoring application might be less affected by the inaccuracy caused by gathering a vehicle's distance slightly late than, say, a driving application. This parameter can be specified once together with the query. For instance, the user can provide the query in a declarative query language along with the parameters as sketched on the following slide. The query and the configuration of ARTC are then forwarded to the sensor device. A read-time tolerance algorithm has to run on the edge device and must therefore adhere to the following execution-specific requirements. Firstly, despite advances in hardware technologies, sensor devices are still restricted in computational capabilities compared to sinks. They need to schedule reads very precisely and are often battery-powered. Therefore, the algorithm has to be energy efficient. Secondly, the algorithm has to be able to adapt to changes in the data distribution quickly. Otherwise, the application might miss important events. Lastly, the algorithm has to be general and not depend on the query's remaining configuration. ARTC is a stateful algorithm which iteratively computes a read-time tolerance for the next sensor reading, which a multi-query read-sharing algorithm can subsequently exploit. We implement ARTC within an existing framework for on-demand data streaming, in which Traub and others introduce techniques for demand-aware streaming from sensor nodes. They aim to acquire and transfer data according to the query's data demand. They define a so-called user-defined sampling function, which the user can implement to specify a query's data demand. The user-defined sampling functions enable the sensor device to iteratively suggest a next read time in accordance with the query's requirements. Secondly, they present a solution for sharing reads and transmissions among queries by contributing a multi-query read scheduling algorithm executed on the sensor device. It uses individual read time suggestions of the deployed queries to then schedule a single read that serves multiple queries. ARTC integrates within this framework and implements a part of the user-defined sampling function, which I introduce in the next couple of slides. A user-defined sampling function is a mapping from the last sensor read time and value to the next sensor read request. It contains, firstly, the desired read time, which can, for instance, be proposed through adaptive sampling techniques, which are a family of well-known techniques that adapt the sampling frequency based on the data's variability. Secondly, an interval around the next read request. ARTC implements the second part of the specification of a user-defined sampling function and hence iteratively computes the read time tolerance. To be less dependent on the read time suggestion algorithm, we divide our solution into two parts. Firstly, adapting the diameter of the read time tolerance interval, and secondly, shifting the interval around the next suggested read time. We record the exponentially weighted moving average of the difference in consecutive readings. We use this quantity to capture the performance of the read time suggestion algorithm well. To ensure that the objective of the retime suggestion algorithm is compatible with those of the retime tolerance algorithm ARTC, we feed this quantity into a PID controller, which then shifts the retime tolerance around the desired retime. The intuition behind using a PID controller in this place is that the retime suggestion algorithm's quality is considered not to be subject to large fluctuations, but to adapt gradually. The current variability of the value difference, on the other hand, lets us infer whether a large retime tolerance could hamper our goal of maintaining the data utility. We reduce the retime tolerance exponentially in the number of consecutive times that it exceeds the user-defined threshold to adjust to changes in data quickly. When the threshold is not exceeded, we linearly increase the diameter of the interval. Our main focus is on designing a lightweight algorithm. By only using 2 instances of a probabilistic exponentially weighted moving average algorithm and a PID controller, we utilize only very little memory. We can compute the next retime tolerance by only performing very few mathematical expressions. We evaluate the performance of ARTC by replaying data from multiple real-world datasets. On these datasets, we configure multiple queries. Firstly, a query which does not perform read sharing at all, but only adaptively samples via the algorithm add-in. Secondly, a query which uses ARTC on top of the configuration of query 1. And lastly, a query which replaces ARTC by a fixed retime tolerance algorithm. By operating based on replayed data, we can compute the difference between the perception of the data we receive by a query configured via ARTC and the dataset's actual data at a higher frequency. During our experiments, we compare the performance of the 3 configurations. Before I present quantitative results on the average read imprecision induced by ARTC, its baseline, and without read sharing altogether, I show an experiment from an exemplary experiment trace and visualize the behavior of ARTC. In this scenario, we gather one-dimensional data from an acceleration sensor. The y-axis holds the recorded acceleration of an individual's torso over time, while the individual conducts multiple activities. We can observe that between the 7 and the 27-minute mark, the acceleration oscillates a lot between -10 and 10 and has got a very high variation when compared to the rest of the experiment trace. This is because the individual performs a sports activity, which produces data that differs a lot from those recorded in an idle state. I present this example experiment trace to visualize how the adaptive retime tolerance algorithm ARTC is able to adapt to such drastic changes in the nature of the replayed data. On this slide, I record the retime diameter, which ARTC dynamically adapts during the experiment trace. We observe that the retime tolerance shrinks during the phases of high variability, effectively disabling read sharing, and increases again afterward. I also added the performance of a fixed retime tolerance algorithm baseline, which I configured to allow for the same average retime tolerance as ARTC. During the phases of low variability, the retime tolerances proposed by the fixed retime tolerance suggestion algorithm are smaller, and during the phase of high variability, they are larger than those proposed by ARTC. As expected, this in turn decreases the quality of the replayed data for the baseline. On this slide, I plot the moving average of the error of the replay data for the 3 settings. The error of the baseline is slightly smaller than those ARTC can report during the phase of low variability. However, during the phase of high variability, the baseline's error skyrockets up to 50% of the data's magnitude. As ARTC is able to reduce the retime tolerances drastically, its performance is at par with the query that does not allow for read sharing altogether. During the quantitative experiments, we ran queries with the 3 configurations you already saw in the last experiment. We compare the average misrepresentation of the data while running ARTC to those of a fixed retime tolerance algorithm, which achieves a similar read sharing potential. We compare the average misrepresentation of the data while running ARTC to those of a fixed retime tolerance algorithm, which achieves a similar read sharing potential. To show that ARTC is able to operate on very different datasets, we select a very volatile dataset, a dataset with phases of high volatility, and a dataset which contains data that change steadily. Throughout the experiments, we observe that ARTC is able to outperform its fixed baseline. To conclude, we devise an adaptive retime tolerance algorithm, which we call ARTC. During our demonstration, we are able to report that ARTC is able to reduce the misrepresentation of the data by up to 60%. We supply our implementation of ARTC and the evaluation in an open source repository. Thank you for your attention.